The fact that we were able to capture still images of life's daily occurrences today is all due to experimentation that scientists have done in the past. Some of us who have taken a photography class in HKIS were curious about the photography behind processing film. Because of this, learning about the chemistry will help us understand why photographic film develops in the first place, along with the steps in which this occurs. The main goal of our experiment is to use different chemical concentrations and see if the film develops. Through the course of this experiment, the preparation and process of producing photographs on a photographic film will be determined along with its chemistry and the impact on processing photographic film on the environment.
The purpose of our lab was to determine the percent of trypsin in a solution that would be the most optimal for photographic development.
The independent variable is the concentration of trypsin in percent. The dependent variable is the clarity of film, which is the range of opacity indicating clarity, and the controlled variables are the temperature of the water, which is 35 degrees Celsius, size of the test tube, which is 100 milliliters, size of film, which is a 35 millimeter film, a type of film, which is the Kodak film, and time, which is 5 minutes per film. The hypothesis of this lab is if there is originally a higher concentration of trypsin, then the film's clarity will be clearer because there will be more enzymes to assist the hydrolyzing gelatin into amino acids.
The equipments are 5 grams of trypsin, 35 millimeter photographic film, which are gelatin coated and cut into strips, 18 100 milliliter beakers, 1 500 milliliter beaker, 1 100 milliliter graduated cylinder, 2 10 milliliter pipettes, 1 thermometer, timer, distilled water, scissors, marker pen, tape to labels, Bunsen burner for hot water, lighter, balance, stirring rod, and tweezer.
Make sure you put on your glasses and aprons for safety.
As for procedure, we first weigh out 5 grams of trypsin on the balance. Then we measure out 95 milliliters of distilled water in a 100 milliliter graduated cylinder and add it into a 500 ml beaker. Dissolve the 5 grams of trypsin into the 95 milliliter of distilled water in the beaker and make the 5% trypsin solution. Label each beaker with the concentration of trypsin to be investigated. Use separate 10 ml pipettes to measure out volumes of 5% trypsin solution in distilled water. Make each concentration in clean 500 ml beakers. Make sure the solution in the 500 ml beakers are constantly kept at a temperature close to 35 degrees Celsius. Maintain the temperature within 2 degrees of this during the course of the investigation by adding more hot water if necessary. Cut 2 centimeter pieces of the 35 millimeter photographic film and and then put it into the test tube. Place the pieces of film into the test tube. Set timer at 5 minutes. After 5 minutes, take a note of the opacity in the data table. Repeat for each concentration trial 3 times for more accurate results.
In our experiment, the clarity of the film was linked to an opacity gradient, in which a higher value equals higher clarity. The results of our experiment were of the following. The film treated in the 0% trypsin solution had an average clarity of 3.33 on the opacity gradient. The film treated in the 1% trypsin solution had an average clarity of 4.67. The film treated in the 2% trypsin solution had an average clarity of 5.33. The film treated in the 3% trypsin solution had an average clarity of 6.33. The film treated in the 4% trypsin solution had an average clarity of 7, and the film treated in the 5% trypsin solution had an average clarity of 8. The following observations were taken during the course of the experiment. As the film was in the trypsin solutions, the tan-colored gelatin began to dissolve. Of all the trials, the most gelatin dissolved off the film in the 5% solution, and the least off the film in the 0% solution. After each trial, the films each had different opacities based on how much gelatin was still on the respective films, with the film in the 0% solution having the lowest clarity, and the film in the 5% solution having the highest clarity. The intermediate solutions followed the same pattern. The gelatin dissolved in order of the clarity of the films was from highest to lowest in the 5%, 4%, 3%, 2%, 1%, and 0% solutions. During the course of the experiment, calculations were done to calculate how much trypsin is needed to be in each solution. For the 0% solution, 0 grams per 10 grams of solution was needed. For the 1% solution, 0.1 grams of trypsin per 10 grams of solution was needed. The same goes for the 2%, 3%, 4%, and 5% solutions with 0.2 grams, 0.3 grams, 0.4 grams, and 0.5 grams of trypsin needed for each 10 grams of solution. The graph and data reflect what we hypothesized in our hypothesis, in which we predicted that the higher the concentration of trypsin in the solution, the higher the clarity of the film will be. The only difference to the hypothetical graph present was that the correlation between the concentration of trypsin and the average clarity was less steep than expected.
Our procedure was very basic, consisting of 6 beakers with different concentrated trypsin solutions: 0%, 1%, 2%, 3%, 4%, and 5% trypsin. These beakers were used for the film to be placed in. With this setup, it was possible to test how different concentrations of trypsin, an enzyme that breaks gelatin down, affected the clarity of the film. Because gelatin breakdown is directly related to film clarity, this lab setup and procedure are very efficient in testing whether or not a more concentrated trypsin solution allowed for more clear or less clear film development.
The light-sensitive chemicals used for the reaction in photographic film are silver halides. Silver halides are compounds formed between silver and halogens such as bromine, chlorine, and iodine. These silver halide crystals, which are within gelatin, are coated onto a film base. When a photon is absorbed by a silver halide crystal, the photon causes the electrons of the silver halide to have a delocalized electron orbital. These delocalized electron orbitals can be attracted to a sensitivity speck, which is a shallow electron trap. When the light is exposed onto the crystal, the sensitivity speck on the surface turns into a small speck of metallic silver. If there are 4 or more atoms of silver available, it is considered as developable, which means that it can turn the entire crystal into metallic silver. However, to begin the process in the first place, an enzyme must first expose the silver halides by breaking down a gelatin.
Enzymes are proteins that catalyze chemical reactions. During these chemical reactions, substrates or beginning molecules are metabolized into products. These reactions can either be exergonic, meaning that heat is released, or energonic, meaning that heat is absorbed. If the reaction is exergonic, the reaction can also be considered catabolic, and if the reaction is endergonic, the reaction can also be considered anabolic. It is good to note that substrates and their respective enzyme collide randomly, meaning that a higher enzyme concentration increases the likelihood of the substrates being broken down. This supports the data in our experiment and why the film was clear when more trypsin enzyme was present to dissolve gelatin.
The enzyme used in this experiment, trypsin, is a protease that dissolves proteins such as gelatin. Proteases, or enzymes that break down proteins, are an extremely important subclass of enzymes. In this experiment, gelatin, a protein which is essentially a series of amino acids, was hydrolyzed with the help of the enzyme trypsin C35H47N7010 to break down the peptide bonds between the amino acids. The product of this reaction was a vigorous group, a number of amino acids, along with the heat that was released as a result of breaking the peptide bonds. Essentially, the chemical equation for this process is gelatin plus H2O yields amino acids.
One possible error that occurred in this experiment was exposing the film to the light. When cutting the film strips, some strips got more exposed to light than the others. This could have potentially altered the clarity of the different film samples after they were placed in the trypsin solutions. Another possible error that occurred in the experiment was that the percent of the trypsin in the solutions was not completely accurate. It is possible that the percent of trypsin made was a little over or under the percentage wanted, which could have slightly affected the clarity of the film samples. To fix these 2 errors, the use of a darkroom and more precise measurements of the trypsin powder for the trypsin solutions could be implemented.
From this project, we were able to learn more about enzymatic function, the chemistry of photography, and how to more effectively set up a lab procedure and apparatus that would be appropriate for different situations.
From the results, it is clear that the higher the trypsin enzyme concentration is, the more clear the film will be, because more enzymes are available to break down the gelatin that contains the silver halides that are integral to the development process.